Hi guys, this video introduces the map abstract data type. This is a abstract data type that we'll look at in a few ways with a bunch of different data structures, the association list, and a few kinds of binary trees. The inspiration for a map is some kind of a lookup table from real life applications. A lookup table is a table or chart. Every row is an association between a key and a value. So for example, this lookup table here has a key column which has strings that are abbreviations of units of measure in the American Standard Measurement System, and the associated value is a floating point number, which is the number of milliliters that corresponds to in the metric system. So 1 teaspoon corresponds to 4.39 milliliters, and 1 ounce is associated with 29.6 milliliters. Another example might be menu prices. So the string burger is a key, and the associated value is 2.99, $2.99. And fries is associated with $1.99. And the way that we use these is if you wanted to search for a price, you would first have in mind the product you're looking for. You would scan the key column and look at the corresponding value row. So if I want to know the price of a salad, I would look in the key column until I find the salad row and then look over at the value. It's 3.99, $3.99. Another inspiration for the map data structure is a mathematical mapping. This is where the word map comes from. It's math terminology from the definitions of functions. This is one way of defining a function in mathematics. There's this notation f:\d arrow r that says f is a function that maps an element of a domain set into an element of a range set. D is kind of the input to the function, R is the output of the function, and they use this verb maps. So they say this function does the work of taking a input and mapping it to a output or converting it. For example, f of x equals x squared is a function that maps any real number, that's the domain, to a non-negative real number, because the way that squaring works is you only get non-negative numbers. So one way of viewing a function f like this is that given an x, f of x finds the value associated with x. So the x is kind of like the key column on the previous slide, and the value f of x is the associated value. So if I plug in 2 as x, f of x gives me 2 squared, which is 4. So that would say that 2 as a key is associated with the value 4 in the right column. Applications of the map come up quite a lot, actually. It's a very practical data structure. We use it all the time in practical software. It's useful anytime we want to associate some kind of key with a value. Usually the key is some kind of identifier, like an ID number or a name of something, something like that. So there were the examples on the first slide. If we were making software that did unit conversions, then it might have that exact map data structure in it so that when we convert tablespoons to ounces or something, we can look up what the numbers that those correspond to. Or menu prices. If we were making a shopping app, then we might use a map to map from a product name into how much it costs so that the cart could work in the app. Some other examples would be authentication. That's anytime you log into a system and you have to provide a username and string, and you're only allowed to log in if the password and username match what's in the user database. So that could be implemented as a map data structure where a key is a string containing a username and the associated value is the string containing the password. And then when you try to log in, the backend server looks up in its map and decides if the password is right. They actually do it a little bit differently for security reasons, but it's kind of beyond the scope of this presentation. Another example is the domain name system. This is what maps a domain name like fullerton.edu into its IP address. IP address is a numerical address that is used by computers to route traffic. Humans have a hard time memorizing these because they're just sequences of binary numbers. So we have these domain names like fullerton.edu, and the domain name system has a map in it. It would probably have a map data structure that says fullerton.edu corresponds to a certain IP address, and CNN.com corresponds to a different IP address, and so forth. Another example would be on your file system. Every file has some associated contents on the disk, and the file system that implements this needs to know, for a given file name, where do I find the contents of that file? So that could be a map. Key is file name, value is disk address of where to find that information. Another one that comes up pretty frequently is counting the frequency of objects. For example, if we wanted to count how many times every word is used in a page, that's a metric that's used in search engines and analytics and things like this. So we could build a map where every key is a string for a word that appears on a web page, and the value mapped or associated with that key is an int for how many times that word appears. And a map data structure would make it efficient and convenient to manage any of these applications. Let's say a little bit more about this terminology because we're going to be using it a lot. A key is an object that identifies one of these associations. So as I mentioned, it's usually an ID number or a string that's a name of something. It could be a human chosen name, like an actual human's name, or it could be the name of a website or the name of a variable or something like that. So usually these keys are either an integer type, int or unsigned int or something like that, or a string. Not always. Other data types are allowed, but often in practice it's usually an int or a string. The requirement for maps to work is that the key data type has to be comparable. In C++, that means that the less than and the equal operators need to be defined. So any data type that is comparable that way with a less than and an equal could serve as a key. So for example, Boolean could work, although it would be a little weird because there's only two possible Boolean values. The value associated with a key is whatever data is associated with that, and it's often a container class. So you might have a map that maps a username string to a class that has a lot of data members representing that user in a web application. But it can be any type, and values don't need to be comparable. So basically any data type in your programming language can work as a value. That's just information that is associated with a key. We don't use it internally in any data structure operations. A pair is a structure, a struct in C++ that holds one key and one associated value. The maps in the C++ library use pairs to bundle together one key and one value. We're going to use that convention in these videos as well. A pair is sketched as open paren, the first value, comma, the second value, close paren. That's the notation that's used in mathematics for a pair. So, for example, if I wanted to sketch the row of that unit conversion table that has teaspoons, the key is the string TSP and the value is the number 4.39. In pair terminology, the first value is that string, the second value is 4.39. So I would sketch that pair as paren string TSP in quotes, comma, 4.39, and then close paren. STD pair is the class built into the standard library. It's actually a struct that represents one of these key value associations. You can actually use it for any pair of things, but one major application of it is a key value association in a map. The full declaration of it is standard pair, type 1, type 2, T1 and T2 are types. Those are template parameters. And that's a struct that holds one element called the first element of type T1 and a second element of type T2. The convention used for maps is that we store one association, like one row in that table, as a pair of the key type and the value type. So a given map will have a key type like string or int usually, and then a value type that's whatever you want. That's what you're associating with those identifiers. So for example, the unit of volume lookup table would use key type as a string, for example, TBSP, tablespoons. Value type is float, like 14.8. So every row of the table, which stores one association, would be a pair of string, comma, float. Okay, in a map, the keys have to be unique, meaning that every key appears only once. That's the same thing as in a lookup table. If a key appeared twice, then the association would be ill-defined, meaning when you look up in the table, you can't tell which one to use. For example, if I changed my food price table like this, now there are two entries with salad. So what's the price of a salad? One row says it's 3.99, the other row says it's 3.49. It's undefined, it's not a useful table anymore. So all maps have this requirement that a key can only appear once, because otherwise what's the associated value? It's unclear. Okay, finally we're going to say what the formal operations on the map data type are. You can create an empty one with a constructor. There's a contains search operation. So contains takes a key as an argument and it returns true if the map contains a pair with the given key, false otherwise. So this is a check. Is this key anywhere in the map? Find actually finds the pair associated with a map. So contains gives you a Boolean. It's a quick way of checking whether a key is even there. Find goes in and finds the whole pair that's associated with that key. So the idea is that there is such a pair, you pass in the key argument, and it finds the pair associated with that key and returns that pair. But if it cannot find that, meaning the key is absent, it throws an exception. Insert is how you put a pair in, so you have to pass the insert operation a pair object that has a key and a value. And if the map does not contain that pair already, that's kind of how it's meant to be used, then we insert the pair and return true, so you know that something happened. But otherwise, if that pair was already present, this doesn't do anything and it returns false. And the return value is how you tell whether we actually accomplished something with that insert call. Finally, erase to remove a pair. Erase is given a key, and if the map contains a pair with that key, we remove it and return true. That's kind of the main way that we use this. But otherwise, if we can't find that key, then the erase operation does nothing and returns false. So you can tell that that's what happened.